Thanks for inviting me. This is work I'm doing with Clara Dessa and Yuko Okumura on dynamic impacts and predictability of Niño and La Niña. So most of the talk is on the dynamics of 2-year La Niña events. So 2-year La Niña events are these La Niñas that last 2 years or even longer, which are pretty common. I'm going to try to show you how common they are. And before these recent months that we are expecting in El Nino, everything that happened, and we said during the last decade, everything that happened in the tropical Pacific were La Niña. So let's get started. There's an outline. Here's the outline. The introduction, I'm going to focus on two overlooked issues about La Niña events. And one of them is the asymmetry in the duration between El Nino and La Niña. This feature of equatorial disease in which cold SSTs, La Niña anomalies, last much longer than El Nino. And then something new that we're looking with Yuko and Clara, which is the impact of 2-year La Niña, are also asymmetric with respect to the impact of El Nino in terms of duration, of course, La Niña, but also in strength. So I want to touch on that because I think that's also new. The methodology, mostly for the dynamics of these 2-year La Niña events, is going to be a heat budget of ENSO events from System4. System4 is a model developed at NCAR. That is one of the few models that can simulate these persistent La Niña events realistically. So we're using this model to understand the dynamics. And what we do is develop a nonlinear version of the classic delayed oscillator equation based on System4. And with that simple equation, we try to identify the mechanism that generates these 2-year La Niña events. And then that's what I will show you in the results. And then also, since we found that it involves the equatorial thermocline, we expect that that could give us some predictability. So I'm going to show some new results in which we started to look at the potential predictability of these persistent La Niña events. But let's start with. So the motivation is, there's 3 motivations. One is ENSO dynamics. We want to understand the dynamics of these events. Also, model evaluation. We want to see if System4 simulates these events for the same reasons that they happen in nature. And also the predictability. I think that's the most important one. And I think it's one that has been somewhat overlooked in the predictability studies because most of the emphasis is on the prediction of the onset of El Nino. Like now, we want to know whether it's going to be El Nino. But the onset of La Niña is trivial. Every La Niña happens after El Nino. But the termination of La Niña is non-trivial, and that's what we're going to be focusing on. Can we predict when La Niña is going to end? Is it going to end on the first year, on the second year, on the third year? And I think that's relevant for the impact, because if you live in a place where, like South Florida and the Southeastern US, there's drought conditions during La Niña, it would be nice to know how long La Niña is going to last, and therefore know how long the inputs are going to last. So these persistent La Niña events are pretty common. That's the time series of the Niña 3.4 index that is commonly used to estimate the magnitude of Niño and La Niña events. And it shows that that's the pointer. Let me go back. That's Niña 3.4 SST anomalies from that region in the Central Pacific. And you see that there's many instances through the historical record in which La Niña events lasted 2, 3, even 4 years after the 97 El Nino. Especially in the 2000s, we had many 2-year La Niña events, 2007 and 8, and also 2011 and 12, that was associated with the terrible droughts in Texas. So it's a pretty common phenomenon that we don't understand why they last longer. Okay. And that's an example of the 2011 12 La Niña, so you see the SST anomalies on the first year and also on the second year, cold conditions in the tropical Pacific, with the typical rainfall anomalies associated with La Niña, with dry conditions in the central Pacific and wet conditions over Indonesia, but you can also see the drought over North America, especially in the southern tier of the United States. So this figure shows how models from different periods in the observational records for El Niño. So we see that all El Niños lead to La Niña. So the prediction of the onset of La Niña is trivial. They always come after El Niño. We see time goes up and longitude along the equator, and we see that all the same features are common through these different periods in the observational records. But when we look at the same composites for La Niña, that's the point there. Maybe I'll do it here. So those are composites for La Niña. And that's where you see the second year La Niña. On the second year, so this is the first year La Niña, on the second year we see how the cold SST anomalies re-emerge. And these are, again, through the 20th century, different observational periods, showing how common these events. Yeah.
Not the figure. Before
this one?
The delta removed the kilo,
no, it's these are only in just anomalies with the.
So this includes the kilo variability.
Yeah, it includes the kilo variability. This is another example where we composite for the 20th century. La Niña events that lasted 1 year and those that lasted 2 years to see the evolution of El Niño and then La Niña, and the ones that last 1 year then they tend to overshoot into El Niño, but then there's the 2-year La Niña events that with cold SSTs coming back on the second year. And the other thing I want to mention is up to 50% of the La Niña events last 2 years in the observational record. So it's a pretty common feature. These are composites of 8 events, 8 2-year La Niña events that occur during the observational record, and you see how starting different seasons, how we start with the preceding El Niño in wintertime there, and then it vanishes and leads the way to La Niña conditions into the second, into the next winter, and then how the cold SSTs persist into the second year, into the winter of the third year. So predicting the return of La Niña is pretty challenging. And these are plumes put together by the IRI, International Research Institute, which show different predictions. So the black line is the observations, and the colors are different predictions made by different forecast systems. And this is a point in summer of 2011, after the first La Niña of 2010-11, when you would have predicted, are we going to have La Niña conditions coming back or not? And that's what you want to know, if in the following winter there's going to be a return of La Niña or not. And what you see is the spread of all the models is all over the place. It's models predicting El Niño, a model predicting La Niña, and if you probably compute the ensemble mean, it will give you neutral conditions. So it's something that it's very difficult to do. It's what makes these La Niña events return. And these are the statistical models, which I would say that also show the same lack of skill predicting the return of La Niña. So the first thing we wanted to do is to understand the dynamics so that we can see if there's any predictability. But the other issue is that the droughts over North America are likely to intensify during the second year La Niña. So what I'm showing here is, in blue, this is the latest figure. In blue is a composite of 4 events during the satellite period. So this is 1982 and 2010. The blue is Niño 3.4 SST. So you follow the first, this is the El Niño that precedes La Niña. This is the first year La Niña here and the second year La Niña. So these are 4 events all averaged together. And when the red line shows rainfall over the southern tier of the United States, and you see that there's weather conditions with El Niño, then there's drought, and the second year drought is much stronger. And there's even a summer drought here at the summer of the second year. And also in red is the soil moisture anomalies. So there's also dry conditions in the soil during the second year that intensify. This is something we don't understand why it happens. I'm not going to explain why, and we still don't know why it happens. We're looking at that. And those were 4 events, but this seems to be a robust feature also of the observations. This is a composite of the 8 events all through the 20th century. I'm showing rainfall anomalies from land stations. So we see that when we start, these are the rainfall anomalies associated with El Niño, which is wetter, southeastern US. And as we go into the first year La Niña, the southern tier of the US gets drier, associated with those with that La Niña event. And in the second year, the dry conditions expand. And almost by the end of winter of the second year, almost the entire country is under drought conditions, according to this composite. But there's really 2 issues if one wants to make progress on this. There's really few state-of-the-art climate models that simulate these events. So if one wants to predict them, I assume that you probably need a model that can simulate these events in the first place. The good news is that the NCAR CCSM4 can simulate them, and pretty realistically, as I will show you. The GFDL models are also simulate these 2-year La Niña events. And the other issue is that if one wants to understand the dynamics of these events, is that the conceptual models are linear, and we will expect that to get an asymmetry between El Niño and La Niña, there should be some nonlinearity or asymmetry in the dynamics that will give rise to that feature. So these conceptual models assume that La Niña is just the mirror image of El Niño. And therefore, if El Niño lasts 1 year, then La Niña should last also 1 year. So the good thing is that we had CCSM4, which we used as a surrogate for the real world to develop a conceptual model that is nonlinear, so it can capture some asymmetries, or it has some asymmetries that could give rise to this dynamic. So this is just to show you that the realism of the SST anomaly simulated by CCSM4. This is a Hope model of equatorial SST. So we have longitude, South America, and the Western Pacific, time going upwards. December 0 is the peak of the first La Niña, so we have the cold SSTs simulated for the first year. CCSM4. These are composites of events simulated by CCSM4, so all averaged together. I'm using a pre-industrial control run, so this is a very long run of CCSM4 that has 13 centuries long. So in this figure, when included 100 composites, 100 events. And we see how the cold SSTs persist into the second year. And this is from hard SST and observational data set also showing the return of La Niña on the second year. And those are the spatial patterns. These are the observations for the 8 observed events during the 20th century. And those are the spatial patterns simulated by CCSM4. So we have El Niño on the first year, then the first year La Niña in wintertime with cold SSTs in the Central Pacific, and then the second year with weaker cold SST anomalies, but much wider and stronger signal in the North Pacific. So conceptual models, as I said, assume that La Niña is the mirror image of El Niño. For instance, the Richards oscillator or the delayed oscillator. And this is a schematic of the Richards oscillator model. I want to show it so that then we can contrast the dynamics that we see in CCSM4 with this linear and mirror image view. So we start with this circle indicates a positive SST anomaly and weaker trade winds. Relaxed tilt of the thermocline in the ocean in this schematic. And these weaker trade winds drive a discharge or a divergence of heat content that shows the thermocline in the equatorial Pacific. So that leads us to the neutral state or the transition into La Nina, in which the thermocline is shallower. So as the thermocline shows, you have colder water from below the thermocline that can be upwell and train into the surface. So that's a negative tendency onto the SST. So that terminates El Nino and drives La Nina because the negative tendency on the surface. And that's how we get to the state in which we have colder SSTs in the eastern equatorial Pacific, which drive also stronger trade winds in this case, and the stronger trade winds just reverse this process, and then the convergence of mass on the equator that deepens the thermocline, and as the thermocline deepens, we get to a state in which a deeper thermocline will drive a positive tendency on SSTs that will get us to El Nino, and this is how El Niño and La Niña oscillate between those two states. But when we look at these two indices of these basic dynamics in CTSM4, we see notable departures for 2-year La Niña events. So what I'm showing here is a composite, again, of Niño 3.4 SSTs in blue. So we see El Nino peaking, then the first year La Niña at month 0. So I'm using month 0 as the peak of the first year La Niña, and then we have the second year La Niña with weaker SST anomalies, but still cold SST anomalies, and then it returns to weakly positive SST anomalies. This is a composite from CTSM4 of all the La Niña events that lasted 2 years. But the difference is on the thermocline anomalies, which are in red, and here I'm showing the zonal mean thermocline anomaly. So this is the depth of the thermocline. And, oh, I had some. So we have El Nino, and El Nino drives the discharge, a shoaling of the thermocline, which we see in CTSM4. We see a shallower thermocline after El Nino. And then that drives the first year La Niña. So all that makes sense according to the linear dynamics of the ENSO cycle. And then La Niña drives the first year recharge, so it's the deepening of the thermocline. So we see here positive thermocline anomalies. But that's when the linear dynamics break down. We get to a state in which we have a positive thermocline, or a deeper thermocline, and cold SSTs that last for 2 years. So this is already saying that the thermocline needs to stay deeper for much longer in order to terminate La Niña. So it's already a hint of a nonlinearity there. So that's the second year La Niña. It's only the second year La Niña that seems to lead to the return to the termination. So we wanted to be more systematic, and this is what I did for my PhD, compute heat budget. So we applied the same methodology for CTSM4. We focused on the linear terms of the temperature equation. But even though we focus on the linear terms, these terms can still have nonlinearity. So just the temperature tendency, zonal advection, meridional vertical advection, and also vertical advection, the other term of the vertical advection. And I also include the nonlinear zonal advection, but I'm not going to show results for that, and RC fluxes. But so the bar, I'm following the convention that prime variables are interannual anomalies, bar variables are the seasonal cycle. So here we still don't have nonlinearities, even though it's a linear equation, because the dependence of U prime on T prime could be nonlinear, or the dependence of W prime on T prime could be nonlinear. So all these three terms that are the terms of the ENSO feedback can still have nonlinearities through the dependence of the prime terms on T prime on this temperature anomalies. So the first term of that I'm going to focus on is the Thermocline term, which is W bar dT prime dV. So this is the vertical advection by climatological upwelling. And what we see is that it mostly follows the depth of the thermocline that I showed in the previous figure. It's a negative tendency leading to La Niña here a few months before the first year La Niña, and then it's a positive tendency on SSTs after the first year La Niña. So this is a term that is analog to the delayed thermocline feedback because it's involving the transition from the different phases of the ENSO cycle. Then there's also the zonal advection term, the advection of the climatological zonal temperature gradient in green here, which plays both a role in the transition, as you see. Sometimes it follows the red line, but it also sometimes is correlated with the blue line. So it has a component that all contributes to the transition to the delayed thermocline feedback, but it also has a component that it's more of a positive feedback. It's correlated with T prime, with the SST anomalies, the blue line, and it's more like the Viernes feedback. And then there's also the upwelling term. So it's the vertical advection by vertical velocity anomalies, which is always correlated with the SST. So it's correlated with blue. Magenta line is correlated with the blue line, so it's more of a positive feedback. So it's a contribution to the Viernes feedback. So what we did is take all those terms, explore any nonlinear dependencies on those terms which are tendencies, and try to match them with the different terms of the delayed oscillator equation. The delayed oscillator equation is here, which is the simplest equation for the ENSO cycle. We have the tendencies, like in our temperature equation, and on the right-hand side, we have this term that is the Viernes feedback because it gives us a positive tendency. A, B, and C are positive constants. So this is a positive term. Whenever we have a temperature anomaly, we'll drive a positive tendency on that temperature anomaly, which will make it grow. And then we have the delayed thermocline feedback, which is it has the minus sign, so it's a negative feedback, and it's lagged. That's why there's a T naught. So it has the memory of the previous event. And then there's the atmospheric, this nonlinear damping that plays the role of the earthy fluxes. So and then there's noise. So those are just what I said. So let's look at the zonal advection and upwelling terms, which we equated to the Viernes feedback. And in this plot, I'm showing them in a different way. I'm just showing the relationship of those tendencies, those heat flux convergences. In this case, I'm plotting them as watts per meter squared. The relationship with the temperature anomalies. So if the model was linear, we should expect here a straight line between these dots. But we see some the slope of this relationship changes. So this is the positive part. A Niño event drive a positive tendency, and that makes them grow. The Niño events here on the x-axis is at the negative SST anomalies drive negative tendencies, which also make La Niña grow. But the slopes of these two quadrants are different. So La Niña events are more unstable. They grow faster for the same SST anomaly than La Niña events. And we also see some dependence with the calendar months. That's why I'm plotting them with different colors. You see that there's a seasonal stratification of those slopes. They're modulated by the seasonal cycle. So in our delayed oscillator, nonlinear delayed oscillator equation, we're going to take that seasonal dependence into account. That's the thermocline term, which we found is involved in the transition between El Niño and La Niña. So what this term, the relationship of that term on the y-axis here with the large temperature anomalies shows is that for El Niño events drive a negative tendency. So that's why this acts as a termination. It means that whenever there's a Niño, some t0 time later, there's going to be a negative tendency shown on the y-axis. And we also see that that effect for La Niña is much weaker. So this is also hint. This could be the answer, because it's saying, oh, the termination of La Niña is going to be weaker. But it also tends to saturate. When you look at these dots in green there, they tend to flatten out. As La Niña becomes stronger, this effect doesn't grow as fast. And this is another nonlinearity. This should be a straight line for this to be linear. And the last thing is atmospheric damping, which also shows a nonlinearity. So these are the RC fluxes, which are also a negative feedback, but it's not a delayed negative feedback. It's just an instantaneous negative feedback. So I'm showing the LC fluxes, the effect of the atmosphere on the SST anomalies, and we see that for El Niño, there's a negative LC flux will tend to damp those SST anomalies, and also for La Niña, there's going to be a positive tendency, but we also see that saturation as we go into the strongest La Niña events. That damping effect doesn't grow as much and as fast. So that's another nonlinearity that could make La Niña events persist longer. So that's the heat budget equation on top, the nonlinear delayed oscillator equation. So the difference in our equation is we keep the same structure, but A, B, C, which are constant in the classic delayed oscillator equation, here are functions of T prime and also of the seasonal cycle. So these A, B, and C are functions. So we fitted those scatter plots to exponential curves, and we derived for each season functions for A, B, and C. A, B, and C are the slopes, the derivative of those scatter plots. And here I'm showing them. So A is not a number, it's this function. That is a function of T prime, and it's also a function of the calendar month. And the terms that contribute to the Viernes feedback, what we see, it makes sense, is what we saw before. El Niño events have a stronger growth rate. So this is A, it's much stronger for El Niño for positive SST anomalies. And it also gets stronger, it's modulated by the seasonal cycle. It's only stronger in the second half of the year when we know the Viernes feedback is stronger. So this all makes sense. And we also see a weaker Viernes feedback for La Niña. So that's one nonlinearity there. Then these are the T dependence and seasonal dependence of the B coefficient, which is positive, but because of this negative sign, it's a damping term. So we see the same thing is that El Niño events are damped more strongly, so we have the bigger values here, but the La Niña events are damped more weakly. So we see, also this is showing that saturation that I described in the scatter plot. And especially towards the end of the calendar month, we see that the values really get close to zero here of those damping rates for the delayed thermocline feedback. And the last thing is the atmospheric damping, which also shows the same type of structure with more damping for El Niño than La Niña. So we have all three candidates that could lead to the persistence of La Niña. So then the next thing we have to do is to play with them, turning them on and off, and in the simple equation, and see which one of these play a role. So the last thing we have to do is to estimate the noise. So we assume that the noise is white and Gaussian. It's like the simple-most assumption. So the only thing we have to figure out is the amplitude of the noise. So here in this plot, I'm plotting on the x-axis the amplitude of that white Gaussian noise, and on the y-axis, I'm plotting the standard deviation of this equation. So if we run it for 20 times for 13th century, just the same length of the system, you can run this equation like in a minute. So the red curve is showing the standard deviation of this equation as we increase the magnitude of the noise, and at some point we have a value of the amplitude of the noise that matches CCSM4 amplitude. So we pick that one. So we have the same standard deviation as CCSM4, which is about 1. The nice thing is that by doing that, we also get this skewness. We didn't do anything to get this skewness, but we get this skewness of this T prime, which is the Niño 3.4 index, but basically developing a model, a one-dimensional model of Niño 3.4 index. So that's nice. We got this skewness. So it's encouraging. But we also got the seasonal modulation of variability. So that was also a good test that this simple one-dimensional equation is capturing features of CCSM4. So this is how the standard deviation of the Niño 3.4 index changes with the calendar month. In blue is CCSM4. We see that there's more variability towards the end of the calendar year, like in the real world. That's why El Niño is called El Niño. And our simple equation with our choice of the amplitude of the noise of 0.23 gets that same modulation, even in magnitude. We get a pretty realistic spectrum in the variance-preserving form here. The same color convention. Blue is CCSM4 with a strong interannual peak, and also these simple equations that simulate it. The dashed lines are the min-max ranges from our 20-member ensemble for the simple equation. We also got the frequency of occurrence of La Niña. I mean, we expected to get this thing. This is why we can use this equation to study the analysis, because we capture the duration of 2-year La Niña events that CCSM4 simulates. So I'm going to explain this figure. It's the percentage of events that last 1 year or 2 years or 3 or 4 in CCSM4 in blue and the equation in red. So we see that we capture that 60% of events last 1 year and 30% last 2 years as in CCSM4. And also the composite evolution of the SST anomalies is quite realistic for these 2-year La Niña events with SSTs of the last 2 years here. So now we can look at the nonlinear controls on the duration of La Niña with this simple equation, because we can turn on and off these nonlinearities and see what's the effect of the duration of La Niña. So this is our control run when all the A, B, and C terms are nonlinear, just from CCSM4. So first we did all those feedbacks linear, and we get rid of the 2-year La Niña. So instead of using exponentials to fit all those curves, we use straight lines. Then we made the Viernes feedback nonlinear. So this is the A coefficient of the equation, and we still cannot with a nonlinear Viernes feedback, but all other feedbacks linear, we still don't get a 2-year La Niña event. So the Viernes feedback nonlinearity is not the cause of the duration of La Niña. Then we made a Thermocline feedback nonlinear and all other feedback linear, and this gave us the persistent duration of La Niña events. And we completed with making the atmospheric damping nonlinear. We get some 2-year La Niña, not as much as with the nonlinearity on the Thermocline. So I think this already answers that nonlinearity in the Thermocline, on the delayed Thermocline feedback, that makes La Niña events persist. Conversely, we get that there's changes in the period of ENSO, which it makes sense, because if you're making La Niña events last longer, that is going to influence the period of ENSO. So we see that the nonlinearity in the Thermocline here in red gives us a much longer ENSO period than all the other feedback nonlinearities that we see speaking here. So this is nice, but how does this Thermocline nonlinearity work? What are the physics or the dynamics of the Thermocline nonlinearity? And I'm going to try to explain it. I find it hard to explain it. But so at least we know which term is the nonlinearity coming from. And is that term the W bar? So we don't care about W bar. It's really this term that it has a nonlinear dependence with T prime. So the nonlinear dependence is there's many things involved between T prime and D. So SST anomalies drive winds, with winds that change the thermocline depth, and then they change the stratification in the upper ocean. So the connection between these two is through those processes. So we found that in C-system 4 is the connection between this term and the depth of the thermocline, or the anomalies of the thermocline, that are nonlinear. All the other connections until we get to T prime are fairly linear. There's this weak wind nonlinearity. So here we have winds too, because temperature anomalies drive winds and drive thermocline anomalies. So there's a weak nonlinearity here that is also in the observation. It's in the observations, but the strongest nonlinearity is here. How those thermocline anomalies influence the stratification anomalies, which eventually are gonna drive this tendency on the SSTs, completing the feedback. So that scatter plot is showing from the model that relationship between DC prime DC. In order to understand this, it's a gradient. I call it more as the difference between the surface and some depth, in this case 90 meters in the subsurface. So that's a temperature contrast in the vertical. So what we see is that for positive thermocline anomalies, so this is the termination of La Niña. So La Niña drives the stronger trade winds drive a deepening of the thermocline, which would terminate La Niña. But we see that at some point these thermocline anomalies here on the x-axis stop driving strong temperature contrast, so this DC prime DC, compared with El Nino, with this other side of the quadrant, when we see that these thermocline anomalies drive very large temperature contrast. So it's that nonlinearity that influences, that goes in here, that makes this, I mean, this is a constant, or a seasonal constant, so it doesn't matter. And that brings about a nonlinearity. We looked at the analysis data, and you cannot see that nonlinearity, or that change in slope between those two magnitudes. So I'm going to keep trying to explain how it works. Yeah.
Can you go to the last one? This scatter plot to me looks like it's much linear. How do you argue it's not linear?
Which one?
In left, for example, the NCAR model.
Here you have.
I know the linear, non-linear is very small to me. It's linear,
you have linear this part. When you get here, you have 20, and you have less than 2. When you have here, you have 20, and you have more than 2. So that's the nonlinearity. It's at the very end. So what I was trying to explain on the next slide is there's a linear regime here, like here. Yes, you have a linear regime, and that's why you have 1 year La Niña. But as La Niña is going to get stronger, you start going outside that region where it's straight, where it's designed, and you start having the nonlinearity. So I'm going to try to explain here how it works. These are even more complicated composites, because I'm trying to show the evolution in time of the vertical structure of the ocean on Niña 3.4. So we have 0, that is La Niña, and this is before and after, and this is depth on Niña 3.4. So it's just the central Pacific. And we see how the cold anomalies are in the subsurface, and they reach the surface, leading to La Niña. And this would be the linear regime. But when La Niña events get too strong, and here we see that there's really big heat content anomalies or thermocline anomalies below the surface, leading to La Niña. So that the subsurface and surface anomalies are very different between the 1 year and 2 year La Niña events. And when we look at the DC prime DC, so here I'm plotting these things, like vertical structures. So I think that this is a better way of looking at this, because we're not focusing on just one depth. We're seeing the entire, and I'm plotting this, the entire water column. I'm plotting this dashed line, which is a mixed layer. So you have to focus above the mixed layer, which is where these stratification anomalies can influence SSTs, you see that for both of them, you have all the same magnitude of certification anomalies. This is the part that matters, not the negative DC prime DC that drive that negative tendency terminating La Niña. So there seems to be a limit at which the rate of the heat content is replenished and La Niña can return to neutral. And it's mostly, DC prime DC. And the way I think about it is, once the thermocline, you can deepen the thermocline some amount, but at some point, as it gets deeper and deeper, it won't influence the thermocline. So that is the surface. So that is the limit. And it only works for the very strong La Niña events, which drive these very strong thermocline anomalies, which at some point do nothing, or the effect that they have on SSTs it saturates, and then because these La Niña events are so strong, then it takes much longer to be damped by those negative tendencies. So that's how I think it works. But so the other thing is that we think let me see what's in there. Yeah, so the conclusions are, from the ENSO dynamics motivation of studying this, is that these La Niña events persist for more than 2 years because this nonlinear coupling between the thermocline and the surface. CTSM4 seems to simulate these events quite realistically. It has that nonlinear relationship in the thermocline, at least compared with the analysis data. We want to explore that more just to evaluate these dynamics, whether this CTSM simulates these events for the same reasons that they happen in the real world. And the last thing we want to know is, for the prediction, is how can we predict these 2-year La Niña events? And I think we have one predictor or one precursor of this 2-year La Niña, and it's how strong, or how strong the first-year La Niña event. It should give us some predictability on the second-year La Niña, or in other words, it's knowing whether La Niña enters that nonlinear regime can give some predictability, because we know that once it enters that nonlinear regime, it's going to be likely to require an extra year to terminate. So we looked at we did some diagnostics on relations between precursors of La Niña. So the first thing you look is, on the y-axis, I'm plotting SST anomalies on the second year. So below this dashed line is La Niña conditions, so negative SST anomalies. And here I'm plotting on the x-axis the magnitude of the thermocline showing during the second year La Niña. So this is what you would look at. The 6 months before, is the thermocline shallow or deeper? And what we see is that there's no relationship. And this goes back to the first figure. This won't be a predictor of whether La Niña is going to last longer, because no matter, even if the thermocline is deeper with flow, it won't be efficient at terminating La Niña. So it's not really a good predictor looking 6 months